Yeah, okay. So, it's sort of a nice segue that Mark talked at the end about giant robotic spiders, because one of the issues with talking about algebraic K-theory is that modern algebraic K-theory is a well-developed subject with an enormous amount of machinery. And watching talks or looking at sort of current work in algebraic K-theory is often sort of like watching a kitten get torn apart by giant robotic spiders. Or maybe it's more sort of like being the kitten. But it's but this is so. I want to tell you in the course of we have a lot of time, and I want to tell you in the course of these lectures something about what that machinery is like and how to work it, and at least how to learn how to become comfortable with it. But I also want to start by emphasizing that the origins of algebraic K-theory and the kinds of issues that motivated this and ideas that help you make sense of what's happening now are very, very natural. And, so if we want to start at the beginning, the idea that motivates all of this So one thing I should say about this talk is I'm fond of giving slogans during the talks, which are sort of moral statements that I hope you remember, whatever else you can recall. So there'll be lots of those. And our first sort of slogan, maybe not with that piece of chalk. Let's try again. The first sort of slogan is that we're going to study a ring R via its category of modules. Okay, so the basic move is that we want to understand a ring, and instead what we do is we study its category of modules. And this is a very familiar idea, right? We see lots of manifestations of this. So for instance, this is a familiar strategy. And let me give you a couple of examples. So for instance, one of them is that we now know that to study a group, we can study representations, right? And a group representation basically is a module. So, and we know that that pays tremendous dividends in terms of understanding the structure of groups. An example that's maybe a little bit closer to things that we've talked about already is that if we want to study a space X, and I'm putting space in quotes because I mean sort of a generalized space, so either a topological space, maybe a compact Hausdorff space, but maybe I also mean a projective variety or something like that, so an algebraic space. If we want to study a space X, we can study the category of vector bundles, suitably interpreted on X. And this, in fact, so we saw in a bunch of the student talks already that you can do this to great effect, right? That this tells you all sorts of interesting things to think about the vector bundles. And in fact, we've seen sort of the moral predecessors of algebraic K-theory. But we can say something precise that sort of motivates where we're going to go with module categories in terms of vector bundles by recalling Swans Theorem. Okay, so Swans Theorem says the following thing, which is that if X is compact and Hausdorff, so now we mean a topological space, then there's an equivalence of categories. Then we have and the equivalence of categories is between vector bundles on X, let's say real, although it's not so important, and finitely generated projective CX R modules. Okay, and let me unpack a little bit what what's going on with this. Namely, what are the terms on the right? So what is this? And also, what is the functor that's inducing this equivalence? Okay, so real vector bundles on X, I'm going to assume we at this point in the workshop that we know something about. But what do we mean by finitely generated projective CXR modules? I'll say something about, I'll review free and projective modules in a second, but let me tell you what this is. So here, CXR denotes continuous, let's not say that, let's just say continuous functions from X to R. And maybe more illuminatingly, what is the functor that achieves this equivalence of categories? That functor is the global sections, right? This is realized, so the equivalence realized by global sections, which we'll write traditionally as gamma. So why do the global sections, so what's a section, right? What I mean is that, let's say a tiny bit about this. So if I have some bundle over X, right, what I want is a map from X back to P such that the composite is the identity, right? And if you think about, so what is this? So it's very easy to see. I mean, this is not, well, I'll say things about the difficulty of the proof of this theorem in a second. But one thing that's fairly easy to see is that a section has a structure as a module over the space of continuous functions. So, or the ring of continuous functions from X to R, what do? Well, you have a map from X to P, and now you multiply. You know that's a vector space, and you multiply by the value of that function at that point, right? And you can add those things, of course, and that's your module structure. Okay, so it's straightforward to see that this is a module. It's not as straightforward to see it's finitely generated projective, and there's some work to show that this is a equivalence of categories. Let me remind you, incidentally, that so actually, raise your hand if you are extremely comfortable with the notion of equivalence of categories. Okay, so that's great. Let me remind you anyway what I want to mean by it. Equivalence of categories, we have a functor f from C to D, and there are various ways to say this, provided that you believe in the axiom of choice. They're the same. And the way that's relevant to the proof of this theorem is that what we mean is that we have an induced map, right, from maps from xy to maps from fx to fy, and I want this to be an isomorphism of sets, and I want every object D in D is isomorphic to f of c. So this is called fully faithful, and this is called essentially surjective. That language will recur. Now, and you can see sort of the other kind of equivalent notion you might give about this is that I have a functor g going back, right, that's an adjoint that induces the equivalence. And of course, if you want to produce that functor from this data, you need the axiom of choice to kind of pick your values. Okay? But that's maybe neither here nor there. Right, so let me say two more things about Swans theorem. So further remarks. One, proof is an exercise. So I'm going to assign lots of exercises during these talks. Exercise usually means something that I think a reasonable person who is attending, given sufficient work, could figure out. And it's also a cover for things I don't wish to prove. So, but I'll try to tell you about things that I don't wish to prove that I don't think that you should feel bad if you can't prove. This you could do. This is not easy, but you could do it. One place to start in thinking about this is within the class of projective modules, of course, we have free modules. And one nice thing to think about is, as a geometric matter, what does it mean if the global sections are free? What is that telling you about your vector bundle? Okay, so that's exercise 2. First exercise, maybe. What does it mean if, gamma of p is free? And I guess I should make that a question. Okay, and you can relate this to geometric things you know about vector bundles. Okay, so that's Swans theorem. And there's a version of this, so at the beginning somewhere, maybe now erased, I talked about other kinds of notions of space. And indeed, there's a version of this due to Serre. Serre's theorem is the analog for algebraic vector bundles. And I think this restricts to over an algebraically closed field. Okay? So now one thing that you see already, so what's the point, what's the lesson of Swans theorem? The lesson of Swans theorem is that even if you think you're nominally interested in geometry, really you're interested in projective modules. Right? That's somehow what you were actually studying. And one of the other things to say, and this is going to be a recurring theme, particularly today, is that one of the things that's really interesting about algebraic K-theory is that it's a locus for having one kind of invariant that captures, depending on what you put into it, captures information about algebraic number theory, about algebraic geometry, about manifold geometry, about topology. And we're seeing that now, in some sense. Right? All of these vector bundles on a scheme, or in a more general sense, perfect complexes, and vector bundles on a compact topological space, or projective modules over a ring, all of these are kind of the same thing. And we're going to be able to feed them into the same machine. Okay, so that's, I think, what I wanted to say about Swans theorem. And let me now rapidly review some details about free and projective modules, with the proofs of these assertions left as exercises. So let's write them down. So I want to, because of the nature of these lectures, I'm going to assume away almost all perverted behavior, but I will try to alert you to places where perverted things could happen. This is now one of those places. So recall, so we're going to fix R is our ring, and we'll think of a free module, or a finitely generated free module, as a module that's isomorphic to a bunch of copies of R. Okay? And these have an obvious invariant called the rank, or the dimension, right, if you're thinking of something of a field. And one thing you would like is that we want n not equal to m to imply that Rn is not isomorphic to Rm. Okay, it's bad and counterintuitive if that happens. Now, this is called the invariant basis property, I think. But in any event, we want this. This is true. Now, if R is commutative, or if R is polynomial, this is true. The places where this is true for basically anything that you deal with. The places where this is not true are, for instance, if you think of infinite dimensional matrices over a field, you can have problems with this. And so if you've ever seen any of these, well, any kind of construction with infinite dimensional matrices, you can get into, and you think about module categories over that, you can get into trouble. Another running theme is that algebraic K-theory is interwoven with smallness conditions of some sort or another for various reasons. And this is related to one of those reasons, although the biggest one is this finite generation issue. And I'll explain shortly why finite generation is essential to what we do. OK, so those are free modules. Let me now say something about projective modules. So we're going to focus on what I'll write as proj R, which is a category finitely generated projective R modules. Now, what do we mean? So let me remind you what we mean by projective. So there are lots of equivalent formulations, right? So one thing, so let's say some facts about projective modules. So of course there's a lifting criterion, which is that if we have a map from P to M, and we map down, and that's a surjection, then there exists a lift, right? That's often the first definition you see. One comment I'll make about this is that this should remind you, this is not a unique lift, and this should remind you of the kinds of lifting properties that we saw in the talk on model structures. That's not an accident, and I'll say more about that when we move into the sort of more homotopical parts of this. But there are other properties of projective modules that are more relevant for us, or at least that I'll implicitly be using, and so maybe I should tell you what those are. So, you know, some other facts. Let's give these things numbers. One, so here's a fact. P is projective if there exists Q such that P plus Q is free. Okay, so projectives are wedge summands or retracts of free modules. This is a very nice criterion because this makes sense in lots of categories, right? You can thinking about the idea of closure under retracts or idempotent completion is a basic and fundamental thing. So we'll come back to this. Another thing to say is that P is projective if the functors P tensor R blank and Hom R P blank are exact. And what I mean by exact is they take short exact sequences to short exact sequences. Now there'll be much more to, exact sequences are going to be a recurring player in our story. And I'll say more and more about them. But are exact. So let me, I guess, write something about that. And what that means is preserve short exact sequences. And short exact sequences may be the most important motivating property from projective modules for our purposes is that, what number is this? Let's call this number 4. A short exact sequence, 0 to P1 to P2 to P3 to 0 of projective R modules splits. Okay, and I'll say this now as foreshadowing. Algebraic K-theory is about splitting exact sequences. If I wanted you to remember one sentence from everything I say over the next week, it is that algebraic K-theory is sort of the universal functor that splits exact sequences. That's what it is. Everything else comes from that. Well, that and some sophisticated ideas about homotopy theory. But, you know, but mostly everything comes from that. And let me just write what I mean by splits exact sequences, of course, or sort of the essential consequence. So what we mean is that 0 to P1 to P2 to P3 to 0, and now we have a section, right? So the composite is the identity. But what that implies is that this sequence is isomorphic in the category of such sequences to this. Okay? It means that somehow there aren't any exact sequences that don't come from the trivial exact sequences that arise from sums. This is something special about the category of projective R modules. This is not true in lots of interesting examples. And we will quickly move into the direction of examples where this is, you know, false. But this is an essential thing that's true about projective R modules. Okay. So now, did I want to tell you anything else about these? Oh, yeah. So let's erase this here. So one thing to note, do you have a question?
Yeah, can I ask you about the logical dependence between the four properties?
I think these are all equivalent. Let's say that's an exercise. I mean, it's easy to see how to prove these from the lifting property, right? Almost everything I wrote here is very easy to establish from using the lifting, to produce your splitting, or to produce your maps back to show that this sort of the left and right exact sequences. I'm sorry?
The hypothesis you put on the three modules?
I don't think you actually need that for these properties. We will want that for sort of good behavior later, but I think that these things are independent of that. But it's possible that's false. That falls into the category of things I can't resolve on my feet and don't know an example for. Okay. So I wanted to say a few more things about finitely generated projective R modules. One of them is that often, or sort of, it's clear that all free modules are projective. So assertion this is easier to prove from some of these criteria than others. I might call your attention to criterion 2. But any way you slice it, this is easy to see. Now, it's a very interesting question, when are projective modules free? Or really, for what are projective modules free? For what are projective modules free? So for instance, if you are working over a PID, then all projective modules are free. Okay? So, examples are PID, all projective. But this is not always true, and we'll see various examples. Sort of an easy way to produce examples of things where you have projective modules that are not free is to think about the Cartesian product of rings. So if we think about, on the other hand, if we think about R equals R1 cross R2, there are two distinguished modules here, namely 0 cross R2 and R1 cross 0. And both of these are projective and not free. Okay? And it's an exercise, and it's a nice exercise. So one thing to say about this is that my general philosophy about teaching for graduate students, and maybe teaching in general, is that the only way you will learn this stuff is if you think through it for yourself. And so most of what I'm telling you is an exercise you should do if you want to understand this. If you don't, that's fine, But these exercises are worth doing. So this is a nice example. In particular, thinking about how to see that these things, it's not so hard to see that these are projective. It's interesting to think about how to see that these are not free. Okay, so the other thing I want to say is you might wonder why we have restricted to finitely generated R modules. Now, one reason is Swans Theorem, right, which sort of gives us a good defense for saying that our subject of interest are finitely generated. But another thing is this thing called the Eilenberg Swindle. And let me remind you of the Eilenberg Swindle now. You should be so lucky in your life to be able to write a paper in which you talk about swindling something away. So the Eilenberg Swindle is the following. So I'm going to write R infinity for a countably infinitely generated free R module. And now the thing that turns out to be true is that, and I actually will, I think, maybe explain the proof of this. So the observation is that R infinity, direct sum R infinity, is isomorphic to R infinity. Okay, which is, and, as more foreshadowing, we're eventually going to want to think about an algebraic structure involving the direct sum. Having apparently non-trivial objects that sum to themselves should suggest that you might be worried about the kind of algebraic situation in which you might find yourself. Now, there's another thing which is bad. So this is bad. And another thing which is bad is that if P is finitely generated projective, P direct sum R infinity is isomorphic to R infinity. Okay, and similarly, if you have a situation where if I add something on, I don't change it, well, that's alarming. How do you see the proof of this? The proof of this is very short and fun and so maybe worth mentioning quickly. So what do we know about P? We know that P plus Q is isomorphic to Rn for some Q, right? The wedge sum and of frees. And now what that means is that P direct sum R infinity is equal to P direct sum. We can write R infinity as Q plus P to the infinity if we want. Right? So, you just keep adding these things on. So, well, it's isomorphic, which if we're writing that out is P plus Q plus P plus Q plus P, and so on. And now we just reparenthesize. So one thing that I'll mention shortly is that the direct sum makes the category of R modules a symmetric monoidal category. And in particular, we have coherent ways of changing coherently isomorphic ways of changing parenthesization. And so this is isomorphic to P plus Q, direct sum P plus Q, right? But that's isomorphic, of course, to R infinity. Okay, so that's the basic move in the Eilenberg Swindle, and that, well, I'll explain why. You'll see in a second why this is extremely bad. Because what are we going to do now? So now we're actually going to get moving and define K0, which is sort of the starting invariant for algebraic K-theory. And so if I wanted to study Proj R, if you want to study a category, the most naive thing you could do is classify its objects. Right? That's the first thing you do. So we might think about considering isomorphism classes of objects. Right? And this is a set. Now, what we know, however, is that the category of projective modules has lots of structure. And I'll say more things about this structure subsequently. But one thing we know is that the direct sum makes Proj R into a symmetric monoidal category. And again, that means that the sum is commutative and associative, and all ways of associating are coherent. So we can ignore parenthesization up to natural isomorphism. Now, this imposes structure on the collection of isomorphism classes. Right? And this should look like a familiar move, right, from the talks on the construction of topological K-theory. So this means that a set of isomorphism classes in Proj R is a monoid. And what's the multiplication? P plus Q is equal to P plus Q, or the class of P direct sum Q. Okay, so we have this monoid, and one of the things that we know from long experience in our life is that dealing with invariants valued in monoids, this I guess is an abelian monoid, I should say, is that dealing with invariants valued in monoids is difficult. And so the idea that's due to Grothendieck is that you make this into an abelian group. Because we're always, the lesson from cohomology, right, is that abelian group valued invariants are easier to compute, typically. And so we can define K0 of the ring R, which is equal to K0 of proj R, which is equal to what I'll write as the group completion of that monoid. Okay, and we've seen some things about this, but let me just remind you what the group completion is here. So if M is an abelian monoid, then a group completion, I should say the group completion, M tilde is an abelian group equipped with a map M to M tilde, which is a monoid map, which we'll call theta, perhaps, such that if I have any map from M to some abelian group G, this uniquely factors through M tilde. Okay, this is the universal property that characterizes the group completion. Now, we also, and it's handy to have an explicit construction of this, and of course it's what you think, or perhaps what you've already been told, namely K0, well, I should write, let's write K0 of proj R equals the free abelian group 1, the isomorphism classes, modulo the relation that the class of M plus N is equal to the class of M plus the class of N. Okay? And that's the explicit construction. Now, let me return for a second, it's even conveniently still on the board, to the Eilenberg Swindle. Suppose that I was working with not finitely generated projectives, but countably infinitely generated projectives. What would the Eilenberg Swindle tell us? You now know how to calculate all candidate K-theory, or at least K0 groups in that setting. And what are they? They're 0. Right? If you have something where, if you think about the equations we have here, R infinity is equal to 0, and since P plus R infinity is equal to R infinity, P is equal to 0 for any P. That's not the world's best invariant. As a true story, I spent some time, this is one of those hoary things that sounds like an urban legend, but I can attest that since it was me, I was there. I spent a lot of time studying homotopy invariant TC and homotopy invariant THH. And it turns out that homotopy invariant THH and homotopy invariant TC are uniformly the 0 group, or the contractible spectrum. But you can, and of course, you can prove very powerful things about these. So similarly here, you want a non-trivial invariant. So this gives us another reason to restrict to finitely generated things. Okay, so now we have K0, and let's see, where do I want to go from here? I want to go to, right, that was good. Oh, yeah, so I now want to talk about what kind of invariant this is. So what do we know, so what are some things that we know about K0? So a first thing to say is that, some things is that K0 blank is a functor on the category of rings. And what is, this is a basic question to ask, right? If you produce a new invariant, you better hope that it's functorial. And it's useful to ask, how is it functorial? This is actually a slightly subtle thing. Or this statement is not particularly subtle, but let me just write down. So the point is that if I have a map from R1 to R2, then I have a functor from proj R1 to proj R2, which is given by R2 tensor over R1 blank. Right? I change scalars. That functor, if you think about it, well, if you remember, we asserted that this kind of thing preserves, since R2 is projective, this preserves projectives, and so what we end up with is a projective R2 module, right? And you can, I mean, if you think about the talk on the Eilenberg-Watt theorem, you know, what are you saying here? I have a bimodule structure. This map induces an R1, R2 bimodule structure on R2, and that gives you a functor. Okay, and K-theory is functorial in that. Now, the part of this that's a little bit subtle is that the assignment, let me put a warning over here, is that the assignment R to proj R is not a functor. Okay, that's a pseudo-functor, and that's good enough for our purposes, and there are tricks you can play to rectify that into a functor, but it isn't. And you have to worry about that a little bit. As an exercise, think about why this is not a functor. But when we might worry a little bit about this when we start taking values in spectra, which is where we're going. Taking values in abelian groups, we don't care. It turns out. Okay, so one thing is that it's functorial. Now, there's a related question. So, of course, the functor I wrote down there has a right adjoint, right? Namely, if I have a map of rings R1 to R2, we can regard an R2 module P as an R1 module by pullback, right? Now, you know, or it acts via that map, right? So you might hope, based on this, that the K-theory or K0 would also have contravariant functoriality coming from this other functor. What goes wrong? Why is that not always true? What might you worry about vis-a-vis this adjoint? Yeah, it's not at all obvious that this preserves projectives. Look at the case of R2. There's no reason that R2 should be a projective R1 module. Right? As we'll see, so I should say that one thing that's going on here is that in a sense that things were said about in the Eilenberg-Watt talk, or in the Morita theory talk, the category of projective modules is in some sense, over a ring, is in some sense generated by that ring, by the module that is the free module of rank 1 that is that ring. And in fact, in a precise sense that we'll talk about a little bit more. And so when you ask questions like this, always think, what happens to the generator? And here, what happens to R2? There's no reason for that to be projective. That, in fact, is a specific kind of finiteness condition on this map. And in the case when that happens, there are transfers. Right? This is very closely related to, in fact, and there are ways to make this precise from a categorical perspective, this is very closely related to issues about the Becker-Gottlieb transfer, which involved some kind of finiteness, if you remember the hypotheses for that setup. Okay, so let me write a little something so there's something on the board. So this only induces a functor if R2 as R1 module, and the key word here is transfer. Okay. So let's say some other things about K0 and its functoriality. What did I want to say? Yeah. Okay, so one other thing that's apparent from the definition is the following. So we have a map, and there's a natural map from Z into K0 of R, right? And what is this map? this map takes this. This is where, for instance, considerations about the invariant basis properties start to have some bite. Right? What does this do? This is, you want this to take n to go to the class of Rn. And so an interesting question is sort of what's the co-kernel of this map? What is the co-kernel? Which is related to the question of which projective modules are not free. Right? Very closely related to that question. So for instance, you know that this map is an isomorphism. If R is a PID, this map is an isomorphism. But in general, it's not. And what's left is extremely interesting. And we'll see, perhaps shortly, hopefully maybe even in this lecture, some examples of where this is interesting. But anyway, this is a sort of important question. Now, one thing to say about all of this, more formally, is that you notice, of course, that we didn't need much from Proj R. Right? To do this construction, we really used very limited. Proj R has a rich structure, right? This is a full additive subcategory of an abelian category, and we'll return to talk about the structure that comes from that algebraic data. But what have we used so far? We've used that we have the direct sum, right? Maybe said more precisely, all we need to do to build KR, we just used the direct sum, or more precisely, the fact that Proj R is symmetric monoidal. Right? We just needed a symmetric monoidal category. And indeed, and this is, you saw this already in topological K-theory, anytime you have a symmetric monoidal category, you can do this. So if C is a symmetric monoidal category, we can form K0 of C analogously, right? You take isomorphism classes of objects, and you quotient out by the, and you take the group completion of the monoid induced by the symmetric monoidal product on the set of isomorphism classes. Now, you might worry, for some arbitrary category, maybe it's too big, and there's an Eilenberg Swindle kind of phenomenon, which is essentially related to having infinite coproducts, right, if you think about it. Or, sorry, having infinite sums, rather. But that does lead me to my next. So there's a very interesting class of examples, right? One thing you note, for instance, any category with finite coproducts is symmetric monoidal under the coproduct. So for instance, let me give you two interesting and very non-algebraic looking examples. So it'll actually turn out, of course, that these are extremely algebraic, but maybe at first blush they look less algebraic than R modules, namely, some further examples of this. One, finite sets and the coproduct. Which is disjoint union. Right? That's something you can take the K-theory of. And you might wonder, what is the K-theory of the category of finite sets? I guess the K0 of the category of finite sets is Z, as you should be able, as an exercise, to prove relatively easily. But when we extend this to more sophisticated outputs, we get something very interesting out of this. Another extremely, so this is a fairly interesting example. I think an even more interesting example is, of course, something that Mike talked about a great deal in his talks, namely, or at least implicitly was talking about a great deal, namely the K-theory of finite G-sets under the direct product, right? Okay, so again. So this has a this is very flexible, and one So one thing we're going to be doing sort of as we move along is expanding the universe of things we can feed into the K-theory functor. We're also going to expand the universe of things we get out of the K-theory functor until we want to be able to take enough stuff to articulate in a good way what the K-theory functor is. Okay, so having done those examples, right. So what I want to do now is talk a little bit about what this actually sees. So I guess that's here. So let me shift gears a little bit and talk about what does K0 of R see. And the slogan here is that, let me write the slogan. Well, let me write slogan and then tell you the slogan and then write it. The slogan here is that algebraic K-theory is a repository, depending on what you put into it, is a repository for algebraic number theory, algebraic geometry, and invariants from manifold geometry. And you can see this already on K0. Right? It's one of the things that's very compelling about this subject is that this construction, which is surprisingly deep, but is very easy to describe, right? You now know sort of much of what there is to know about at least the definition and construction of K-theory, or K0, and there will be other K groups soon. But already K0 encapsulates all sorts of stuff. And so let me talk about, so I want to talk about two examples. One example coming from algebraic number theory in terms of the Picard group, or the ideal class group, and one example coming from manifold geometry in terms of the wall finiteness obstruction. Okay? So I'll proceed to tell you something about those things. Let me write down the slogan, which is that K-theory is a repository for invariants from algebraic number theory, algebraic geometry, and manifold. Although, if we're perfectly honest, what we really mean is high-dimensional manifold geometry, as you'll see. Okay, so let's talk a little bit about the Picard group. So in the connection with algebraic number theory, we can make a definition, which is that the Picard group of a ring R is the group of invertible R modules under the tensor product. And let's assume here for a while that R is commutative to make things easier when dealing with the tensor product. So what do I mean by invertible? So what this is what we mean is that M is invertible if there exists n such that M tensor R n is isomorphic to R. Okay? And this turns out to form this constraint. There are lots of different definitions I could have given of this. This one is an easy one to write, but puts a lot of burden on the reader in the sense that it's actually true that R, not R, sorry. Let's erase this here. M is invertible implies that M is finitely generated projective, for one thing. And in fact, what the Picard group in any sort of geometric setting you should think about as rank 1 line bundles. And I'm going to write that so that it's on the board for you to remember if you're interested. I don't actually want to develop what that means here, since we don't particularly need it. But this is rank 1 line bundles, if we're in a setting where you can make sense of that. And you might wonder, what is the inverse of a, so in what sense is this a group? So, the inverse, it turns out, is given by the linear dual, R from P to R. Okay, and if you know anything about, and I should pause for a second, if you know about Spanier-Whitehead duality, or any place where you can make sense of duality phenomena, you can talk about an analog of the Picard group. This is an extremely general notion. This makes sense in essentially any symmetric monoidal category where you can talk about duality. Both transfers and Picard groups can be expressed in that formalism with essentially similar definitions. As an exercise, you might check if R is invertible, that if I tensor this with, with P, what I get is isomorphic to R. So OK. So now we're here. And the thing to say is that, and how much did I wish to say about this? Well, let me say the following thing, which is that this is a fact. And this is harder. And again, I'm not going to prove it. But this one, it's less easy maybe for you to do as an exercise unless you sort of know how this all works already. But if R is a Dedekind domain, right, which you recall means an integral domain, so no zero divisors, and we have factorization of prime ideals, then pick R has another name. It's what you might know as the ideal class group. Right? If you think about fractional ideals, so these are sort of submodules of the fraction field, then those have a group structure, and it turns out that's isomorphic to the Picard group. Okay, and the ideal class group is a thing of classical number theoretic significance. Right? So what's a good example of this? It's like the ring of integers in a number field. Right? So we have that, but we also have the following observation. Which is that, here's another fact, which is that K, if R, once again, is a Dedekind domain, then K0 of R is isomorphic to Z, direct sum, the Picard group of R. Now, I'll say just a word about, again, I'm not going to prove this, and I apologize for not proving these things. I mean, the thing of this is we could spend a happy week working out sort of all the details of some of these connections to number theory and to the wall finiteness obstruction. The purpose of my telling you these sort of zapped-in facts is that whatever it is that you were originally interested in, one of the underlying messages is you should probably be interested in algebraic K-theory. Because these examples subsume whatever invariant you could possibly have wanted to know about. So anyways, let me at least give you a map, though. So why is there a connection? And the answer is, and let me say something else as a slogan, the study of algebraic K-theory is closely connected to the study of linear algebra. And notions from linear algebra will recur, at least for a while, throughout our discussion. And so, why is there a connection? The answer is the determinant, essentially. So if you take M is invertible, you can form the nth exterior power of M, which again is a quotient of the M-fold tensor. And again, if you know what this is, that's great. And if you don't, that's fine too. And that construction, it turns out, this provides a map or a homomorphism from pic R to k naught of R. Okay, so sorry? N is the, so if you think of this projective module, that's the, I think that's the rank. Ooh. Did I screw that up? Yes, of course I did. Thank you. Let me think about this for a second. What did I actually, let me see if my notes can help me. No. So do I want to map, so do I want to take R and take its rank and then take that to the exterior power of that rank, and then that should be invertible? Yes, that seems better. Okay, thank you. Sorry about that. Okay. So that's, right. So that's one kind of connection. The other thing that I wanted, right, so having, right, so this is one classical invariant that turns up in K0. The other classical invariant that I wanted to talk about today, and I think will probably be the last thing that I talk about over the remainder of the talk, is the wall finiteness. Obstruction. Okay, so for this, it's useful now to remember that on projective R modules, we had additional structure, right? Projective R modules are equipped with a notion of exact sequence. And let me say something about this. So Proj R is a full subcategory of R modules. And R modules is an abelian category. And in particular, we know what we mean there by kernels and co-kernels, and so we know what we mean by exact sequences. So this is abelian. And so we know what we mean by exact sequence. Now, we can, using this, we can induce a notion, the commonplace definition is that a sequence is exact in Proj R if it was exact in R mod. And well, again, I'll develop this notion a little bit of an exact category and categories with exact sequences subsequently. But let me just say the following thing, which is that now, which is that if C is a category equipped with some class, let's call it E, of exact sequences, and I don't even require any properties of this right now. All I'm going to say about the exact sequences are that they're, things of the form ABC, which are specified in E, and I'm going to require that they're closed under isomorphism, okay, for sanity's sake. So for now, all we'll say is that these are closed under isomorphism. But then we can make the following definition, which is that we'll say now that K0, we give that a name, yes, C. So now we extend the definition of K0 of C, right? We say that this now is, well, again, I'm going to give you an explicit construction and a universal depiction. Let me start by, in this case, maybe giving you the explicit construction. This is the abelian group, or this is the free abelian group on the isomorphism classes. And now we're going to quotient out by the relations that an exact sequence A to B to C implies that B is equal to A plus C. Okay? So we're going to quotient out the relations from the exact sequences. Now, in the situation when when C is projective R modules, this is nothing new. Right? All exact sequences split, and so already we have all of these relations. But, you know, what is this doing? So that's an explicit construction, but there's a universal property which is getting us much closer to sort of the way you might want to think of K-theory as characterized in general by a universal characterization. That wasn't a great sentence, but the thing to say is that here K0 of C now is the universal target for maps from C to abelian groups that take A to B to C to equations B equals A plus C. Right? So this is another way of saying this. So I'm sorry? No, I mean a function. So what I mean here is that K0 of C splits exact sequences. And what do I mean by split exact sequences? If I have 0 to A to B to C to 0, and in settings where that look anything like projective R modules, and we'll be more precise about what we need for this to be quite true, this is the same now as this. Right? In the kind of free group in the kind of construction you've done here, you've forced B and A plus C to be the same. So you've lost the ability to distinguish between sequences that were exact and sequences that weren't, which maybe you had before. And let me put this all in quotes because we're not quite ready to make this into a precise statement. Now, what's an example? So let me say a couple of things. This business about splitting exact sequences, we know classically a functor if it looks like this. What this should remind you of, for good reason, is this should remind you of the Euler characteristic. Okay? And there's an intimate connection between algebraic K-theory and the Euler characteristic. So let me develop an example a little bit more so I can say this. Suppose now that C is the category of finite CW complexes. And here, I'm going to define a notion of exact sequence. So let's say that A to B to C is exact if A to B is a cellular inclusion. Right? So it's a cellular map that's just an inclusion into a subskeleton. And then C is the actual quotient, which makes sense here. Now, it's very far from being true that all of these things split, you'll notice. Now, in order to form one point that you'll note, which makes this a particularly rich example for us, is that you don't, if you think about what kind of K0 group you would like to build, you don't wish to restrict the isomorphisms. Right? These are spaces, and we're talking about cellular inclusions. So what we're going to say is that K0, we're going to extend our definition, and this is ad hoc, but again, I'll put this in an axiomatic framework, that K0 of finite CW complexes is homotopy equivalence classes now. So the thing we're going to say is rather than working with isomorphism classes of spaces, we'll work with, M, maybe I should say that as not M, but X are homotopy equivalence classes of complexes, or I'll say the free abelian group on this mod, sort of the relation coming from the exact sequences. And in this case, if you think about, what do you know about the Euler characteristic on finite complexes? Well, let's review something about what the Euler characteristic is in this setting. So there are many ways to define the Euler characteristic. One of them that is sort of relevant for us is that, we'll define chi of z is equal to the sum from I equals 0 to n of minus 1 to the I of the rank of, the I chains. So the cellular chains on Z, right? That's just the number of cells in that dimension. And this is not obviously homotopy invariant by any stretch of the imagination, but it's a fact of homological algebra that this is also equal to, so this is an n-dimensional complex, incidentally, which is where the n is coming from. This is the same thing as minus 1 to the I times the rank of the homology of Z. Okay? And that fact, which is a piece, something that's true because of sort of easy calculations in homological algebra, that tells you that this is a homotopy invariant. And I'll say as a side note that the category of complexes. So if you think about, how do you get the homology of a space? You take a complex of free Z modules, or free, R modules, if you're working with cohomology and coefficient in R, and it has a differential, and then you take the homology of that complex, right? And this idea that sort of categories of the complexes carry topological information is going to be very important for us going forward. So category of complexes will be a recurring character. Now, this is the Euler characteristic, and one thing you can prove now, incidentally, let me say something about the Euler characteristic in connection with Mark's talk. So Mark talked a lot about the very rich and sophisticated algebraic tools you can use to detect attaching maps in CW complexes. Right? That's what a lot of that stuff is doing. Here, we've wantonly decided to ignore that information, right? We've thrown away information about cell attachment. We're basically just taking some sort of alternating sum of numbers of cells. And so this invariant has lots of, I mean, for one thing, this means this is a very weak invariant, as you know if you've ever calculated the Euler characteristic. On the other hand, it means that the Euler characteristic has lots of nice properties. And one of the properties of the Euler characteristic is that, you know, if A to B mod A is a sequence where this is a cellular inclusion, then a counting argument tells you that chi of B is equal to chi of A plus chi of B minus A, right? Just count. And this looks suspiciously similar to things we've seen before. And in particular, the Euler characteristic factors through K0. So what this says, so one thing you can say actually is that this uniquely, as it turns out, this uniquely characterizes the Euler characteristic along with a value on the sphere or on 2 points or something like that. So you need some ground for your induction, and then, you know, CW complex is made out of spheres and disks, and so you can proceed off to the races. But what we see is that in some sense, the Euler characteristic lives in K0 of finite CW complexes. OK, so I bring this up because I think I'll probably start with this next time from the look of the time. The Wall finiteness condition, which is related to the question of, you know, a very interesting question is, I give you a CW complex, is it of the homotopy type of a manifold? Right? This is a basic classification kind of question. And, it turns out you know things like it's got to be, it's got to be a finite CW complex. But it also turns out that sort of an interesting question to ask has to do with retracts in the homotopy category of finite CW complexes. And you want an instruction to telling you when a retract of a finite CW complex is itself finite. And that, as we will see, is precisely given by a class in K0 related to the Euler characteristic of a certain complex we'll build. Okay, and that's what the wall finiteness obstruction is. Okay, so let me tell you a little bit about where we're going, and then we can eat lunch. So today, and I think from the looks of how things, the sort of speed with which I'm going through the material, on Wednesday, we'll talk about these sort of elementary examples. So K0 and K1 and a little bit of K2 with a focus on understanding how these things are connected to invariants you might care about. So lots of examples of this form. At that point, we'll then shift to thinking about, on the one hand, one lesson that you should learn from this week, speaking of slogans to learn, is that if you see an invariant that takes values in a billion groups, you should suspect that what you're seeing is a spectrum. Right? A spectrum is a sort of topologist's abelian group. And we will enrich the output of our machine to produce spectra rather than just abelian groups. And these abelian groups will then emerge as the homotopy groups of those spectra. Okay, that's thing number one. Thing number two is that one of the other slogans that I want to communicate is that algebraic K-theory is really about homotopy theory. So there's a sort of secret, maybe not so secret now, hegemonic message in all of this, which is that at the beginning I argued, and if I may say so myself, I think compellingly, that if you want to study, let me finish, if you want to study a ring or something like that, you study its category of modules. Right? Modern algebraic geometry is about this. All of this sort of symplectic topology in the Fukaya category, these are all categories of modules. And in fact, they're stable categories of modules. And I'll say something about what that means. And the perspective I want to articulate is that really you want to do that in a way where what you're studying is the homotopy theory of the category of modules. And we can't do that yet because our mod is too weak to possess homotopy theory. And we're going to enrich it, and that's where this notion of complexes is going to come in. We're going to move into a context where we can do homotopy theory, which is very closely related to this sort of talk about abstract homotopy theory and model categories that we had yesterday. And also, we're going to see some talks, I think, this afternoon about abstract homotopy theory from the perspective of enriched categories. And so sort of the output is an objective homotopy theory, but the input will also be objective homotopy theory, and it's in that context that we can best understand what it is that K-theory is doing. Okay, that was a lot to say and maybe remember, but we'll unwind this as the week goes on. So that, I think, is it for today.